All right, today we're heading to Kaabong, Uganda to look at a project that's, well, it's about a lot more than just a new power plant. We're talking about building a new future, literally from the ground up, one that's totally self-sufficient, sustainable, and completely sovereign.
You know, for places like Karamoja, progress has always had this silent handbrake on it, a really unstable power grid. I mean, think about it. The flicker of a light, the insane cost of diesel, just that constant uncertainty. It makes building anything, businesses, schools, hospitals, incredibly difficult. You just can't build a strong future on a foundation that could literally crumble at any moment.
And this is where Project Umoja, which by the way means unity in Swahili, gets really radical. See, the goal isn't just to plug a hole in the power grid, not at all. It's about creating an entire self-sustaining economic ecosystem. Think of it like a living organism, where energy, agriculture, and industry all feed into and support one another.
But here's the wild part. This entire grand vision, right, this super high-tech solution for energy independence, it all starts with something that looks, well, remarkably simple. What you're looking at is dried hemp hurd. It's just the woody core of an industrial hemp stock. So the big question is, how on earth does this become the key to powering a sovereign future?
Well, the answer is in this beautifully elegant closed-loop system. You know, most of our world runs on a linear model. You take resources, you make something, and then you create waste. This is the exact opposite. It's a circular blueprint where every single output becomes a valuable input for something else. Absolutely nothing is wasted. So let's walk through how it works.
Okay, so the whole journey kicks off in the field with cultivation. Pretty straightforward. Then the crop gets harvested and processed right there, on site. Next, it goes through what's called thermal conversion to create fuel for the power plant. But, and this is key, it doesn't stop there. The byproducts are valorized. That's just a fancy way of saying they're turned into valuable new products. And then finally, the leftover nutrients go right back into the soil, completing the loop and getting everything ready for the next harvest. See? It's a perfect circle.
Okay, so let's dive into that first stage, because it's really the agricultural engine of this whole project. You might be asking, why industrial hemp? Why build this whole system around that specific plant? Well, it turns out it's pretty much the perfect choice for a model like this.
So, for starters, it's a fantastic carbon sink. As it grows, it's literally pulling a huge amount of CO2 right out of the atmosphere. Super cool. It also actively improves the soil it grows in. But here's the real clincher for this project. It's an incredibly high-yield biomass crop. That means you get a ton of fuel from a pretty manageable amount of land. And that creates a fuel source that is 100% local and totally secure from any crazy global price shocks.
Okay, so how much fuel are we actually talking about here? Let's put some numbers to it. Based on all the agricultural analysis, a well-managed crop can produce a pretty realistic average of 3.5 tons of this dried hurd feedstock per acre. That number, 3.5 tons per acre, that's really the core metric for this whole operation. And now, to put that into perspective, this is where you really see the scale. To keep just the initial 1 megawatt bridge power plant running for a whole year, the local farming cooperative is going to need to cultivate about 2,000 acres. Now, that's a significant amount of land for sure, but it's an entirely manageable agricultural operation that directly fuels their own local energy independence. It's amazing.
All right, so we've grown it, we've harvested it, let's move to the next stage. Once that hemp hurd is all dried out, it goes to the technological heart of the project, the plasma gasification core. This, my friends, is where the real alchemy happens.
Okay, now it's really important to get this next part straight. This is not burning. It's not incineration. A better way to think of it is like molecular deconstruction. Inside this oxygen-starved chamber, you use extreme heat to just rip the hemp herds apart at a molecular level. And in doing that, you convert that solid biomass into a clean, combustible fuel called syngas.
And when we say extreme heat, we are not kidding. The temperature inside that plasma reactor core can get hotter than 5,000 degrees Celsius. Just to give you an idea, that's hotter than the surface of the sun. This incredible temperature is the secret sauce. It's the key to both the efficiency and the sheer cleanliness of the whole process.
Okay, so you're probably thinking, if this tech is so great, why isn't everyone doing it? And that's a fair question. The answer is because taking this from a cool idea in a lab to a reliable 24/7 industrial power plant is incredibly hard. There are a few major scientific challenges that have just plagued biomass gasification projects for years.
And here it is, the big one, The main problem, identified by tons of independent university research, the project killer. It's one word: tar. It's this sticky, gunky, complex byproduct that can clog up pipes, destroy expensive engines, and basically bring your entire power plant to a grinding, expensive halt. Seriously, if you can't solve the tar problem, your project is doomed from the start.
But this is where the Umoja Project's engineering just brilliantly shines. It's a system that was specifically designed to solve these exact problems. So, that inconsistent moisture issue? Bam! A dedicated module uses waste heat from the system to perfectly dry the hemp. What about precise process control? They've got an AI-powered digital twin, basically a virtual copy of the whole plant, that constantly analyzes data and makes tiny adjustments to keep it at peak efficiency. And the biggest problem of all, tar? Remember that crazy high temperature, over 5,000 degrees? It just doesn't let tar form. It's instantly vaporized, gone. It's a perfect example of how the research identified the problems and the engineering came in with targeted solutions.
Okay, so we've got the fuel, we've got the incredible technology, but what does this all actually produce? This is where the system's genius as an economic model really comes into focus. Because believe me, it's about so much more than just generating watts.
Now, let's be real. Building a system like this is not cheap. It requires some significant upfront capital. As you can see, the core plasma tech and the power generation engine itself, they make up the biggest chunk of the cost. But, and this is a huge but, the project is designed from day one to generate returns from a whole bunch of different streams, which makes that initial investment super resilient.
And here's the crucial point. They're not just selling electricity. That's just one piece of the puzzle. The project is specifically designed with multiple revenue streams. So, get this, the outer fiber of the hemp stalk, that gets sold to the textile and construction industries. The harmless glass-like slag that comes out of the gasifier, that gets sold locally for road construction. And because the whole process is actually carbon negative, they can even sell verified carbon credits on the global market. It's a truly diversified, robust economic model.
And that brings us right back to that core idea of a circular economy. See, when every single output, even the leftover ash, is seen not as waste, but as just another valuable product waiting to be used, well, zero waste stops being some feel-good marketing slogan. It becomes a fundamental principle of the engineering and, just as importantly, the business model.
Okay, but let's be clear. No project this ambitious is without its challenges. It's not all smooth sailing, so let's take a balanced, strategic look at the road ahead, because we have to consider both the massive potential and the very real hurdles this project has to overcome.
On the one hand, the project's greatest strength is its complete sovereignty, the fact that it grows its own fuel. That is a game changer. You combine that with its carbon negative potential and you've got massive opportunities. But on the other side of the ledger, that high initial cost is a major hurdle. And here's the interesting paradox. Its biggest strength, that deep connection to local farming, is also potential vulnerability. The entire system depends 100% on a successful harvest, year after year. And that makes it vulnerable to all the usual farming risks, like a bad drought.
So all of this leaves us with one final powerful question. The technology is proven, the economic model is incredibly sound, and the need for it, well, that's undeniable. So, if Project Umoja can pull this off, if they can succeed in Kaabong, could this become more than just a single isolated project? Could this be the blueprint, the actual replicable model for how communities everywhere, not just in Uganda, but everywhere, can build their own prosperous, self-determined, and truly sovereign futures?